Since the visas for all authors of this work are still under check, we regret that we won't be able to attend the conference in person to deliver the presentation. Instead, we have prepared this recorded video. Please feel free to reach out if you have any questions. Now we will present our paper, A Position-Aware Approach to Decomposing God Classes. I will introduce our paper from the following 4 aspects. We first explain the concept of God class refactoring. The term code smells was coined by Beck and Fowler to represent that designs in source code that may reduce the readability and maintainability of software and need refactoring. And refactoring is a systematic process of restructuring existing code, altering its internal structure without changing its external behavior. People remove the code smell by specific refactoring techniques. There are many kinds of code smells, including long method for unreasonable method size, feature envy for method in the wrong class, code duplication, God class, and many other code smells. God class is a typical code smell. God classes are huge classes that do too much and taking a lot of responsibilities, which means they violate single responsibility principle and take multiple responsibilities. God classes have many negative impacts on software, including, first, difficult to read and understand because of its complexity, and second, difficult to be reused because of useless code and unnecessary coupling, and third, could be modified frequently because of associated with too much responsibilities. The key idea in refactoring God class is to decompose it to multiple smaller classes with single responsibility. There are some refactoring operations that can do this, including extract class, which creates a new class and moves the relevant fields and methods from the old class into the new class. Or extract subclass, which creates a subclass and move that subset of features into the new class, and extract superclass, which creates a superclass and move the common features into the superclass, and so on. After refactoring, the God classes should be decomposed to 2 or more classes that take single responsibility, that obey the single responsibility principle. There are challenges in automatic refactoring God classes. It is hard to divide God classes because various functions fulfilled by different methods often intertwine closely, making it difficult to cut them off clearly, and it's also hard to evaluate the quality of the refactor result. To this end, we proposed our approach. First, we analyzed some real-world God class refactoring example and discovered an interesting pattern. Let's look into the example from the open-source application and media server. The class stream source REST service is composed of 25 methods and 8 fields. The developers decomposed it into 2 smaller classes, and the elements marked in brown are extracted into a new class while the others are kept. This is the 2 classes after refactoring. The marked elements make up the new class called REST Service Base as a parent of the origin class Stream Source REST Service. Observe the origin class. We found that the extracted elements are located in a few successive blocks. 3 blocks of successively located methods were extracted into the new class. That is, the 10 extracted methods are not uniformly distributed across the document, but gathering in 3 consecutive physical regions. Also, physically adjacent methods were frequently classified into the same classes. Among the 24 pairs of the adjacent methods, only 1/5 were broken by the class decomposition. Based on the observation, we formulate 2 hypotheses. First, physically adjacent methods or fields are likely to be allocated to the same class during God class decomposition. And second, during God class decomposition, developers often extract entity blocks instead of individual entities. In order to validate the hypothesis, we analyzed the behavior of adjacent entities in 54 real-world God class refactoring. Up to 85% of adjacent methods are allocated into the same new class, while the number falls to 59% for randomly selected method pair. In 50 out of 54 God classes, adjacent method pairs were at least 20% more likely to be allocated to the same classes. This leads to the conclusion of hypothesis 1. Physically adjacent methods or fields are likely to be allocated to the same class during God class decomposition. For hypothesis 2, on average, 13.7 methods are extracted, where 94% of the methods are extracted with their neighbors. This shows that methods are often extracted in blocks. The size of the extracted blocks is also considerable, which is average 4.8 methods per block. These statistics are similar in fields, which leads to the conclusion of hypotheses too. Developers often extract entity blocks with successive methods or fields instead of individual entity. Based on the hypothesis, we proposed our new approach. Our approach mainly contained two parts. First, analyzing the code to be refactored, and computing the similarity between methods in the God class based on methods function, position, and code metrics. Then, we used these method similarity in our clustering algorithm to decompose the God class to smaller classes. Let's start with the computation of the three similarities between methods. We embed the source code of every method into a digital vector using a sentence D5 model trained on Code SearchNet, and the resulting vector may represent its functional information. Then we calculate the cosine similarity between two vectors and then normalize to 0 to 1 to get the function-based similarity between methods. For the position-based similarity, we assign a number to each method in the order of declaration, and then use the reciprocal of the difference in their corresponding index as the position-based similarity. Metrics-based similarity is computed in two parts. First is the SIMD metric, which measures the overlap of instance variables accessed by two methods, computed as the equations below. Second is the CDE metric, which measures the call-based dependence between two methods, computed as the equations below. At last, the metrics-based similarity is the combination of above two metrics, which is defined as the average of SIMD and CDE value between two methods. Second part is the clustering-based decomposition. It contains 4 steps. First, function-based clustering. In this step, we cluster the methods in the God class by a graph-based clustering, which treat each method as a node, and edges are made depending on the function-based similarity value. Like the figure shows, methods are presented as circles and methods in same cluster are marked with same color. We can further present this figure like this, which sort the methods by their position in code. In this example, a class containing 12 methods are divided into 5 clusters in the function-based clustering. The second step is position-based clustering. We first split the method clusters by their position. As this example shows, the cluster marked in yellow has been split because the last method is not consecutive with other methods in same cluster. Then, we merge the adjacent singleton groups. For example, the cluster marked in green, cyan, and pink each contains only one method, and they're adjacent, so we merge them into one new group contains 3 methods, resulting in 4 groups of methods after this step. In the similarity-based merging, we calculate the overall similarity between groups based on all 3 similarities. Then we keep merging the most similar groups until only 2 groups left or all possible new groups are both too big in size and too far in relationship. As the example shows, in this step we merge the 4 groups into 2 new classes, which finish the clustering of methods. We allocate fields to new class based on access at last. We first count field access statements and methods and allocate each field to the most accessed new class. Some field may not be accessed by any new class or has equal access times. We leave them to the second step, which assign them according to their neighboring fields. To this end, we get the final refactor solution. We verify the effectiveness of the proposed approach through a series of evaluations. The projects from our dataset were sampled from top 1,000 Java projects on GitHub. We filter the commits that contains God class-related refactors and manual review and revise them to exclude the commits that not aim at refactoring or not God classes. We finally collected 133 real-world God class refactoring for evaluation. We reused the metric MoJoFM in our evaluation, which is designed to measure the similarity between two partitions that can be used to evaluate how close the solution is to the reference solution. MoJoFM ranges from 0 to 1, 0 for the worst solution and 1 for the same solution, which is better. Our research question 1 is, can ClassSplitter improve the state-of-the-art in the decomposition of God classes? We evaluated the average MoJoFM for the results given by 4 approaches. We can see that ClassSplitter resulted in substantially greater MoJoFM than the baselines, while Bevettas outperformed the other 2 baselines. ClassSplitter's improvement in method clustering is even larger. We also requested developers to manually rank the best two approaches and the reference solutions suggested by the original developer according to the scoring rules shown. From the table, we make the following observations. First, solutions suggested by ClassSplitter were often preferred by developers. On 78% of the cases, its solutions were preferred. Second, the solutions suggested by ClassSplitter are considerably good, between good and acceptable. Third, the ranking of reference solution is 3.15, suggests that the scores are positively related to the quality of the solutions. Our research question 2 is, how do different types of similarities employed by ClassSplitter influence its overall performance? We disable one of the similarities at a time and repeated the evaluation. The conclusion is, all of the employed similarities are useful. The position-based similarity had the greatest impact on the overall performance of ClassSplitter. Exploiting similarities had a greater impact on the clustering of methods than the clustering of fields. Our research question 3 is, to what extent will the performance of ClassSplitter decrease if we replace the complex clustering with the traditional distance-based clustering algorithm? We did our experiment with the traditional distance-based clustering algorithm, where distances are computed as shown. The average MoJoFM was reduced from 53 to 44, which means customizing the clustering algorithm improved the performance by 20%. We conclude based on the analysis that customizing the clustering algorithm is critical for the performance of ClassSplitter. Finally, I will summarize our paper. We propose a novel approach, ClassSplitter, to decomposing God classes, which is the first one that exploits the relative positions of methods and fields. And we present a new dataset containing 187 validated real-world God classes and their reference solutions applied by the original developers. Both are available on GitHub. Thanks for your attention. For any questions, please contact the authors shown below.